All right. So, and I'll be writing most of the code on the board. You guys already know how it is. So the routine, don't feel embarrassed to ask questions. Just stop me if there's something I'm explaining that doesn't make sense. I'm speaking gibberish or it seems like that. Stop me and just ask me and let me know if you want me to re-explain something. But also, of course, we want to keep discussions centered around the topic that we're on, and yeah, that helps us stay at a good overall time range. Workshop. So by the end of this workshop, so by the end of this hour and a half we have together, um, you will have a strong foundation in both object-oriented programming and an essential understanding of data structures and algorithms. Um, so the table of contents for today, as you know, each session follows the same structure pretty much. Key concepts, we're going to be going over sorting algorithms. I'll just briefly define them like I've been doing with other concepts. Just give you a formal definition, something that you can refer to as this is what it is. And in an exam, asks you what it is, this is what it is, that's the definition, and then I'll explain it to make it more understandable. I'll go over stability, which is an important concept in sorting algorithms. Then we'll go over two of the main sorting algorithms. In the previous semester, we went over five in total, um, and that's a lot. It would be very difficult to get through that in an hour and a half time span, so only going to go over the easiest one, bubble sort, and the hardest one, or what I think is one of the hardest ones, merge sort. Then we'll go over real world applications, and then a code demo and exercise. Okay. All right. So sorting. Uh, so how would what's the first thing that comes to mind when I mention sorting? Filtering. I wouldn't necessarily call it filtering, but because what filtering would do is it would exclude some parts of the data, right? Ordering, yeah. Rearranging, yeah. That's those are good synonyms to sorting, yeah. Yeah. I mean, my point is, it's pretty straightforward. Sorting algorithms are just a procedure to um, order a data set based on some criteria. So when I say order by, does that ring any bells? In SQL and databases. So sorting is an essential part of databases. And it's these sorting algorithms that I'll show you that are examples of things that will be that are implemented in database management systems like Postgres and MySQL to sort data efficiently. There's many ways to sort things in computer science. Some are extremely inefficient, whereas others are are up there. Or all right, I'll write it down. So give you this formal definition, right? Sorting is a method or a method in computer science by which we can rearrange data based on some criteria, right? Okay. And when we talk about sorting, we come across this concept of stability. Um, so what stability is, let's just give a formal definition for stability. Just formally define it. So stability is actually no. Before I do that, one person, at least one person, give me their what they interpret as stability, just in context of sorting. Okay, yeah. So I'm going to reiterate that it is and then I'll explain it. It is the ability of an algorithm, a sorting algorithm, to maintain the relative order of equal elements. Now, what does that mean? Let's take let's create a set of data here, right? I'll use blue as well. Someone give me some random numbers, like 6 random numbers. 4 and 10. Let's add 22 here, okay? And then add 22 here. So just imagine, we haven't gone into how exactly we can implement a sorting algorithm yet, but assume we have some sorting algorithm, right? And we tell the sorting algorithm to sort this data from ascending order. So all the elements that are smaller to the left and larger to the right end of this array, this list that we have here, okay? So as we do that, the algorithm should, through whatever procedure it's using, depending on what sorting algorithm it is should eventually reach an outcome where, in this case, 2 is the first element, followed by 4, 8, or sorry, 6, 10, and then 22 and 22. We have 2 equal elements here, which we're also including in this algorithm. But what we want, what makes for a stable algorithm, a stable sorting algorithm, is an outcome where this 22, which is relative to this 22, comes before, is still in that order. So we want this blue 22 here to in the output come before this 22, retain that relative order, even though they're the same elements. And I think part of the reason why this is important is because usually you may sort by some category, you may sort some set of data based on a category within that data. So you may sort by a person's ID, and for each ID, there's a bunch of other data associated with that ID. It's not just a number. In this case, I essentially gave this piece of data extra data by coloring it. So it has a color value of blue. So 22 with a color value of blue is in an order where it comes before 22 with no color value or color value of black. If that hopefully that explanation makes sense, because that's one thing that you should 100% keep in mind, to be able to distinguish between stable and non-stable algorithms, because that is 100% going to come up on the exam. It did, and I was so glad I knew it. Maybe ID wasn't the best example because IDs have to be unique. So ID wasn't a good example. I think what you're asking is, because each ID is going to have a different value, where does stability even apply? Um, Maybe if it helps, just discard that ID analogy I made, because it has to do with unique data. You know that you're going to have one ID that's completely unique from any other ID. Say you were sorting by transaction amounts. So someone made some account has each account that you've made. Maybe you have a table for a user, and each user has an account table for all the transactions they've made, right? And you want to sort by those transactions. Maybe a user has has made a transaction for 200 euros, 400 euros, 300 euros, and you want to sort by those transactions. In that case, the data, each transaction, there's no constraints ensuring that they're unique. So you may have a situation where you have multiple transactions for 200, but you want to sort in such a way that it's predictable, it's consistent. You know that it's not going to, just because they're the same value, just arbitrarily move them around, because these these transaction accounts may have other data associated with them. So bubble sorts, It's basically it's basically an algorithm where for each element, let me just write it down. For each element, a comparison is made. Comparison is made no matter what. Is made between it and the succeeding elements, and the lesser of the two is sorted. If you're trying to sort in such a way that you get an ascending ordered data set, the lesser of the two would be swapped to. So let's just say if the element is smaller, if the element is smaller, it gets swapped. Yeah, exactly. You're already getting into um, another aspect of sorting algorithms, which relates to the fact that you always traverse each element at least one time. Not in all sorting algorithms, but typically. And that basically means because in order to sort the data, um, you effectively have to traverse each element at least one time, right? So basically, no matter what we do, usually, I know there's some sorting algorithms that are different, but the majority of sorting algorithms will not be able to have time complexity that's better than linear, because you always have to traverse each element at least one time and then compare it with one another. I don't know if I'm targeting your question, but it brought up another part that I wanted to touch on regarding sorting algorithms. Okay, and for bubble sorts, to dive into it a bit deeper, the thing about that distinguishes bubble sort from other sorting algorithms is essentially how inefficient it is. And what that means is that if you have a data set, right, an owner data set, and it gets 8 random numbers, let's put that like in the center somewhere, so because it's 100% going to be larger. So 1082. Yes. Okay. All right. So if we were to perform bubble sort on this data set that we have, what bubble sort is going to do is it's going to define two iterators, right? It's going to define two iterators, two pointers, let's call them that. Let's call one pointer pointer I and another pointer pointer J, right? So these are two pointers. So I and J. And it's going to I and j are going to iterate for a maximum of the number of the length of the array. So let's take the length into account. The length is 1, 2, 3, 4, 5, 6, 7, 8. So we have a length of 8. Length equals 8. So they're going to iterate for a maximum of 8 iterations. All right? Usually in the algorithm itself, we'll do 8 minus 1. So I is going to start. It's going to first start at maybe 0, right? So I is going to equal 0. And while I equals 0, the j iteration, j performs all the iterations throughout the array. So j is going to iterate through each array. J is going to go from 3 to 5 to 8 and so on. And every time j traverses this array, it's going to look at the two elements that it's on. It's going to take into account j and j plus 1. So let's say this array is called array, or let's call it list, sorry. List. So this is list at j, and j equals what? j equals which index? So we have 0, 1, 2, 3, 4, 5, 6, 7. We're at the start, so what would j equal? J would equal 0. And I think an easier way to do this is because I'm trying to explain the entire algorithm as it would be in the computer. But for now, let's just erase I and just think of one iterator. Just think of the fact that we have j, which starts at 0 and has to iterate through the array. Every time j is at, it traverses to a new position, it's going to take its value. It's going to take its value, so that would be the list at index j. And what is j again? 0. So what's the value at j? 3. So 3, it's going to compare it with, so say comp with the list at index j plus 1. So what would that be? What would the value at the list at index j plus 1? Yeah, the index. The index would be 1, so the value would be 2. So it's going to compare. This is how we're going to tell the computer to look at. You're asking how we're able to get the computer to single out two values each time and compare the two in the array. This is how we do it. We first have an iterator that'll iterate through the array, and every iteration we define these two variables. We define list. We define list at index j and list at index j plus 1. So tell me what the value is that you're on and the value next to that value. Okay, then compare those two values. And then in this case, if we detect that the list at index j is larger than the list than the element that comes next, so 2, so 3 greater than 2, we tell the algorithm, first define a temporary value. So define the temporary value, put the list at index j into that temporary value, so put 3 into that temp value, and then make the list at index j equal the list at index j plus 1. So it's 3 at first, so make it equal to 2. And then take the saved temporary value, which holds the value that was j, the list at index j before, and set that equal to the list at index j plus 1. That's how we perform a swap. All we're doing is we're swapping 3 and 2. We're just swapping them. This is just a method that you can use in programming to swap elements. First, you save the elements. You save one of the elements, and you set the element that you're trying to swap with to that element. Then you take the temporary value you saved and set it to the element that was just swapped. The wording may be a bit may seem a bit jumbled, but hopefully that's clear, right? And what the algorithm is going to do is it's going to do that for each of these elements in the array. All right, it's going to do that for each of these elements in the array, right? And then once it's done that, it's going to consult. Let's go back to our example of having I as one of the iterators. You usually have two iterators. You have I and j. It's going to. So by this point, j has been 0 to 8. So to 7, sorry. Once j becomes 7, once we've iterated, we've reached the last value. I is going to iterate for the first time. So throughout j's iteration, I has been 0 the entire time. So now I iterates and becomes 1. And this starts a new cycle for j to iterate again. So it's going to go through again, swap any values it sees where it sees that an ordering needs to take place. And then once it reaches the end, I is going to equal to 3. Yeah. I is going to iterate again. And then after I iterates, j is going to iterate through the entire array again. It's going to iterate, swap the elements again, and then I is going to equal to 4. It's going to do that until it reaches 7, right? And what I think you've noticed is that by doing that, you're essentially telling the algorithm, go through the length of the array for as many elements in the array squared, even if the elements are already sorted, even if the list is sorted. Because by the third time that J has gone through the list to swap the elements, there's a very high likelihood that the list is already sorted, right? It's still going to keep on doing that until I equals 7. Does that make sense? It's a little bit abstract. Um, it's we're getting into nested loops, which can be a bit tricky. But once you expose yourself to it, it'll become easier to understand. What was your question? How do you reassign? How you swap values, essentially? Yeah, and that's what we did here, where we set a temporary value. So I'll just go through it again. Let me get a cleaner slate, so it's less messy. For when we actually implement this, the way you would set it up is you'd have a for loop, and this for loop is going to be for I in the range of 0 until the length of whatever list you're using, right? So say our list was 9. So the loop is you're going to set it up in such a way that the loop is only going to go on until it reaches the length of the array, right? That's how you would stop it. And just to give you a sneak peek on the code implementation, remember our I is the iterator that only starts iterating after J has iterated for the length of the array. And the way we accomplish this is we have a for loop, this for I in range 0 to length list, and we have another for loop inside that for loop. So every time this for loop is done, this for loop can iterate once. And every time, so let me finish it. So for J, we have in range 0 until the length of the list as well. It'd be list minus 1, because yeah. So we'll have this for loop that goes on every iteration once. So this I variable can only iterate every time this is done iterating, right? So like I feel like the way I was explaining it with the 2 iterators at the start was a little bit clanky, because it's kind of it's easier to show with code, but hopefully that part is clear. And the main takeaway from this is that for bubble sort, it's highly inefficient. What's the if we were to evaluate the time complexity? I'm going to give you examples of some time complexity. So we have linear, we have quadratic, we have logarithmic, we have what else? We have constant. What time complexity would you say bubble sort has? Let's talk about each time complexity. So I'll start with constant. Constant is denoted by O of 1 because we have a scale of n and time, relative time. And what constants denotes is that it doesn't matter what the size of the number of elements in your data is. The time will not change. It will remain constant. It will stay the same. I don't care what n is. That's why there's 1 in here. It'll stay the same, right? So constant is the best time complexity you can ever have, because it's not going to change regardless of how many elements you have in the data. And then let's go up to linear time. So linear time states that with each element in the data, the time is going to increase an equal amount. Hence this diagonal graph, right? So if you have 4 elements in your data, I will take 4 operations to complete this algorithm, right? If n equals 4, the time complexity, you could say, equals 4. Although Again, I want to denote we don't usually use values in time complexity. It's just a way to get a relative idea of how long this algorithm takes. We don't usually use actual values for it. That's why we use n. We refer to n usually, right? And then logarithmic time. Logarithmic time states that with each element in the data set, say your data is 8, the time it takes will increase logarithmically, right? That's for a binary search, right? Yeah. Um, and keep in mind, every time in computer science, when we discuss logs, the log is always just assumed to be base 2. We don't usually write the base, but you just assume it's base 2. In math, we assume it's in base 10. Okay? So it's log base 2, and our n, let's say our n is 8, our number of elements is 8, it's going to increase logarithmically. So our output is going to be how much we need to power 2 by to get 8, which is 3 exactly, right? What if we have 7? Then we'll get a decimal number. Yeah, exactly. But the thing is, I'm inputting values here just to help you understand time complexity more, but you don't usually do that. You just refer to log of n. You don't refer to a log base 2 of 8. It's not something I don't think it's not something you'll be asking the exam to do. All right. I think logarithms are pretty easy in general. It's just you have to find how many times the number is divisible by another one. Right? Yeah, that's one way to think about it. The way I like to think about it is just taking the base into account. If you have a base of 2 and you're logging to 8, for example, you're just looking at how much you need to power this base by to get this 8 number, right? So, it would be 3. And you were mentioning exponential time. And exponential time is like it's not the same as quadratic time, even though they're both raised to exponents. But usually, when you're denoting in big O notation, when you're denoting exponential time, the exponent is usually another variable in whatever data set. So you're taking into account the number of elements in the data and some other variable as well, and that's what you set to the power, right? So if this other variable, let's say it's x, right? X equals 5, and your number of elements equals 8, your time complexity would be 8 to the power of 5, which would be really bad. So exponential time you want to stay away from that. I haven't even explained n squared actually. So quadratic time, I kind of talked about exponential time, but quadratic time, it's going to be the number of elements. So let's say our elements are 8. We're gonna keep on using 8. Our elements are 8, right? 8, and the time is going to be order of 8 to the power of 2. For linear time, the time would have been just 8, the number of elements. This time we have 8 to the power of 2. Where you get 64, right? A massive jump. And thus, our time complexity is going to look something like this. So it's going to be increasing very quickly. And now back to our original question. I originally asked you, what do you think that the bubble sort time complexity is? Having reviewed time complexity, can someone give me a guess? Quadratic? Yeah, exactly. It's quadratic time because what we're doing is we have our we have a for loop with the variable I. For I in range, just to reiterate to the way we'd implement the algorithm, for I in range, 0 to the length of the whatever list we're using, right? Then again, within this for loop, we have another loop ongoing for j in range 0 until the length of the list, right? Another loop ongoing. So basically, we're going to iterate through this list. Let's say our list is eight elements long, so 8. We're going to iterate through it, technically 7 times because the range it's going to stop at 7. The range just cuts off it essentially stops right before the maximum range you specify. It's going to stop at 7. So J is going to iterate 7 times, 7 times. It's going to iterate, and then I is going to equal 0. It's going to iterate 7 times again. I is going to equal to 2, or to 1, sorry. It's going to iterate 7 times again. I is going to equal to 2. I is going to equal 3. J7. I is going to equal 4. J7. I is going to equal to 5. I is going to equal 7. It's going to do that 7 times. It's going to iterate 7 times, 7 times. And what we call this is a nested for loop. So you have a for loop nested within another for loop. Every time J iterates through the array, it's always going to keep on comparing and reswapping, even if it reaches the points where the list is already sorted. Maybe by the time J's been iterated for where I equals 3, you've already iterated through the list 3 times already, and the list is sorted. The algorithm is just going to keep on just iterating through it regardless, and that is incredibly inefficient. That's why bubble sorts is that's why we get quadratic time complexity, because we're iterating 7 for the number of elements times the number of elements. Okay, hopefully that's all clear. Okay, right. So moving on, we have bubble sorts. Let's move on to merge sort. Okay, so so we had bubble sort. What's the first thing that comes to mind when you think of merge sorts? Feel free to read it. I don't mind. So let's give a definition for merge sorts. So merge sorts is a sorting algorithm which recursively, so we're going to dive a bit into recursion here. So does anyone remember recursion from a discrete math? Yeah. Yeah. No, that's a way to interpret it, I think. It's not exactly what this is, but and when we're talking about it in the context of functions, like you said, it's when one element depends on another element. Functions, recursion basically refers to us taking a function and calling that function within that function, calling a function within a function. And that leads to this recursive trail where where the function keeps on calling itself over and over again until some base case is met. And that should remind you of a for loop, of a loop, essentially. We're creating a loop, but recursively by calling a function over and over again until a certain condition is met. And that's useful for situations like this where we want to implement merge sort. Merge sort is a sorting algorithm which recursively divides arrays or data sets, let's just say arrays divides arrays before comparing and rearranging the data elements, right? Okay, that definition makes sense. All right, so say we had an array. I'm going to put this in array in like boxes. All right, I'm going to put this into 8 boxes. So 1, 2, 3, 4, 5, 6, 7, 8. 8 boxes, and let's say we have just random numbers, 2, 1. Can someone help me out here? 3. We got 3 twice here. Yeah, no, let me keep it simple and just have unique elements. So let's put 5 here. All right. So what bubble sort would have done is it would have looked through, it would have iterated the list and iterated it multiplied by the number of elements. So it would have iterated it square for the length of the list squared. So it would have iterated, come back and iterated, come back and iterated through each of them, comparing them and swapping them over and over again until it's done that operation 7 times. Okay, done that set of operations 7 times. What merge sort will do is it'll look at this list and it'll cut it in half. Yes, it's a recurring thing. We cut data sets in half very often to make them more efficient, breaking the solution down into a smaller problem. That's the kind of trademark of merge sort. It's a divide and conquer algorithm. So we divide this array in half, right? So we're going to have 2 partitions here. We're going to have a partition with 4 elements, so 2, 1, 3, and 32. Then another partition with another 4 elements, so 5, 17, 12, and what was this one? This was 6. Yeah. All right. It's going to do that. It's going to do it again. It's going to cut them in half again. So we have these partitions. It's going to cut these 2 partitions in half once more. We're going to have 2 more partitions. So we're going to have 2 and 1, 3 and 22. We're going to have 5 and 17, 12 and 6. Okay? And so after that, it's going to partition them again. All right? Does this structure kind of remind you of something? As you have a tree, right? So this is why I wanted to review the previous things we've done, because in a way, like a lot of the efficient algorithms usually end up looking kind of the same, right? Yeah, exactly. Because what we have here is now this list that we've divided into just individual elements in their own little mini arrays with one index. So 2, 1, 3, 2, 22, 5, 17, 12, and 6. Okay? It's going to divide them until it reaches that point. And now it's going to, it has its work cut out for it, because first it's going to look in each pair it has, each pair of arrays it has, and it's going to compare them and order them, right? It's going to look at this pair, for example. So 2 and 1, it's going to, let's put them here. It's going to look, it's going to see that 2 is, going to see that 2 is larger than 1. Add 1 to this, to a sample, a temporary array first, and then add 2, right? And then it's going to see that 22 is going to sort to these 2 as well. So we're going to have, it's going to essentially, once it's done recursing to this point, it's going to move back up, all right, to the point where we have an array with 2 elements again, from 2 arrays with 1 element to an array with 2 elements, right? But this time we have it sorted, right? It's going to do the same here. So we're going to have 3 and 22. It's going to do the same here, and we have the same order. We'll have 5 and 17. And for here, we'll have 6 and 12. And once again, it's going to look at this, it's going to recurse back to this point. It's going to look at these 2, now we have 2 mini arrays with 2 values in them to compare, but we know they're both sorted. So it's going to be much easier to determine which position or how we're going to add them together. We're merging them. We're merging them together, merge sort. So it's going to take these two, 2 and 1, 3 and 22, but here we sorted them, 1 and 2, 3 and 22. It's going to determine a new temporary array. It's going to sort them. So it's going to look at this array and look at that array. So 1, look at this array and look at them both again. 2, 3, 22, right? And because they're ordered, it's what you're going to notice in the algorithm is it's taking less steps to sort the data than it would have had it not done this, had it not split them into these mini partitions beforehand. Okay, and the same is going to occur for this as well for 5 and 17 and 6 and 12. So we're going to compare them both. See that 5 currently has the lesser value. It's going to put in 5 first. It's going to compare them again. It's going to see that 12 has the lesser value. It's going to put that in. It's going to compare them again. Oh, sorry, it has. Sorry, see it's 12. 6 has lesser value. Then it's going to compare them again. Find 12, 17. Now we've merged these two arrays. Now we have two even larger arrays, which will once again merge. So we have our final array. This is what we're going to return. And we're going to compare these two mini arrays. We're going to see, and what you'll notice is that they're already ordered respectively to one another. It's going to look at this array, see that 1 is the smallest value at the first position. And then this, something I should have made clear is that in the algorithm, we're going to have iterators as well. We're going to have iterators that'll check, so just pointers that'll check the values. So first it's going to check the values at the first index of these mini arrays. It's going to see that we input 1 because between these two, 1 is smaller. And this pointer is going to point here instead, okay? So now it's going to compare this to this first value here. This pointer hasn't moved because you haven't inputted the value. It's going to input 2. The pointer is going to move again because it's just inputted a value. It's going to compare the two. 3 is larger, 3 is smaller than 5. We'll go here. It's going to move the pointer again. It's going to see that 5 is smaller than 22. It's going to input 5. It's going to move the pointer, compare the two values at the pointer, 6 smaller than 22. So it's going to input 6. And then for this value, it's going to check 12, 17, and 22. That's how it sorts it. That's merge sort. So the reason why we do all this is because it's just all around more efficient, because what we're doing is we're dividing the array into its own partitions and then sorting those arrays within those mini arrays. Okay? We divide the original array into sections. And once we've reached the point where the arrays are just single values that we can compare with one another, we compare those two and create mini sorted arrays from those mini arrays. And then as we reach the point where we have more and more mini arrays that are sorted, we can then simply merge those two sorted arrays as we move up this tree that we've created. Right? We're moving back up, but this time we've sorted each mini array, merged it, sorted those mini arrays, merged them again until we reach the point where we have our final sorted array. And this is much better than bubble sorts. Yeah, exactly. That's what we're trying to accomplish. We're trying to reach a point where we have each of the arrays, the point where they just have a single value before we rearrange them, right? And ultimately, that reduces the amount of rearranging we have to do. And it also makes it such that we're only rearranging elements if they're actually out of order. We're not doing any unnecessary operations. And the time complexity we get for this is a log n. Okay? So you can think of it like this, where we're breaking down the operating space in half every time, but we still have to iterate through we have to take into account each element no matter what. So ultimately, we're sorting all the elements. So we're going to visit each of the elements at least once. Okay? So this is your first linear logarithmic algorithm, merge sorts. And it's one of the more efficient algorithms for sorting. Yeah, I think this will make a lot more sense because I'm trying to transcribe it into a board. This is one of those situations where it'd be better to actually see it in code. But I just wanted to give you like just an introduction or a visual of what's going on in the computer before I actually show you the code, which it can be confusing to see it and um, yeah. Um, so yeah. So a quick real world application. I think I already mentioned it. It's used a lot in databases. That's where you'll see sorting used very actively. Um, for the order by function in SQL, I believe the Postgres SQL order by uses some implementation of merge sort as well. Merge sort is used in a lot of different algorithms just because of how efficient it is. And yeah, so that's one real world application that you can keep in mind. And search engines as well. So search engines may, for example, you type something into Google, um, the search engine is going to first query based off of a certain category, and within those categories, it's going to determine what's most likely relevant to your query, and order those selections and show you what's at the top of the selection. So that's another implementation of sorting algorithms. Like search engines, basically, um, search engine is going to look at what you're querying. It's going to query from that category, and it's going to sort that category based on what's most relevant to what you're searching for. Does that make sense? Okay. So yeah. So now I'm going to go ahead and stop the recording, and we'll do a quick code demo. So I'll